Right, so part two, this is the extended answer section. So let's have a look for, this is the year 11 yearly chemistry. Let's have a look. So here they're asking us to sketch an energy profile diagram of a reaction between hydrogen and chlorine. Nothing happens initially until it's exposed to light. All right, so first, and then there's a violent explosion is observed. So violent explosion, it's exothermic, and the exposure to light triggers it, which and that's the activation energy. Okay, so remember your diagrams. It says here it doesn't need to have a scale, but that doesn't mean that it doesn't have to have things like an axis. I mean, it's best to use a ruler even, but so this is energy, and you could say this is time. We know a typical energy diagram. In this case, it's exothermic, so it's going to start up here and finish. Now it's quite explosive, so what we're looking for is the relative size of this graph. That's something we've got to account for. So exposure to light is it's just a little trigger, so there's only a little activation energy compared to the large explosion. Okay, so we could say this is delta H, and is energy, activation energy. Okay, so what's your justification? I'll write it up here. Okay, so activation energy is small because it's the light. Explosion is exothermic. Delta H is negative and large. And if you got 1, 2, 3, 4, that would get you there. Question 21. Continued. Write a balanced chemical equation for the reaction using structural formula. Okay, so you could start off just like Cl2 plus H2 gives us what was it? Right. So let's start off like that. Cl, Cl, H, H, and we're going to end up with HCl. So HCl, HCl. Okay. Now the reason they're getting you to draw this here is to realize the bond energy. So here's the bond energy, and if you remember, delta H is equal to the sum of the bonds broken less sum of the bonds formed. If you think about it in terms of your energy diagram, we've got H 2, Cl2, and then these break apart, atomize, and then they reform. Okay, so how much energy is in this H2 bond? So let's have a look at this. So we've got well, there's one of these that we've got to break. So 4, 3, 6, and then there's a Cl bond, a ClCl, 2, 4, 2. That's the energy required to break the bonds, less the energy required to form the bonds. HCl here, so 2 lots of that. And okay, so let's see what that is. 4, 3, 6 plus 2, 4, 2 minus 2 lots of 2 plus 186. Look at the units, kilojoules per mole. Just check what else we need. Okay, that's good. Okay, 22. So we've got some metal. Test 1. We put the metal on your tongue, copper and zinc. This time the metal's touching. And then test 3, you've got silver and zinc. The first one, there's no sensation. Second one, there's a zappy, uncomfortable tingling. And then the last one, there's a sharper sensation. Firstly, why is this not allowed at school? I mean, just any safety thing. So tasting is not allowed. Risk of poison or toxic metals, contaminants. Okay. Describe the principles. So what are we trying to do here? You got to demonstrate for 3 marks that you understand what's going on. So why is there a zappy sensation? Well, this relates to your galvanic cells topic. So in test 1, well, let's say in test 2, a galvanic cell formed. And I mean, if you can demonstrate knowledge with a formula, go and do that. Okay, so which one are we talking about? Copper and zinc. Copper and zinc. Okay, so the voltage has to be positive, so zinc's going to oxidize. So you could write that out. Oxidation of zinc. Zn2 plus 2E. The voltage would be 0.76 volts. Reduction of copper. And that is 0.34 volts. Total cell potential 1.1 volts. Formed. Okay, so I'm demonstrating I know something about galvanic cell. Okay, so it's formed as the circuit is complete with metals touching in test, hence electric sensation. Test 1, no, not touching, no cell, no no reaction, no sensation, something like that. All right, question 22. Now they want to count for differences in test 2 and 3. Okay, test 3 was with silver instead of copper. If you look at silver here, we've got a larger cell potential. So you have to do the same thing now, but just demonstrate that this is a larger cell potential. Test 3. We've got zinc oxidation, Zn2 plus 2E, and we've got 0.76 volts. Reduction of silver, Ag plus 0.8. Add those together. Okay. So 1.56 volts is greater than 1.1 volts of copper zinc cell, hence more current, more sensation. All right, so you're trying to demonstrate a lot. A lot of the answers had most of this stuff, but like if you didn't write down the equation, you're missing the opportunity to demonstrate what you know. Okay, ethanol is a fuel. They give us a density. Okay, and so in complete combustion. So let's write that down first. If you're not sure where to start there. Liquid plus oxygen gives us complete combustion. It's just carbon dioxide and water. All right. So calculate the mass of air. So we need to firstly, all right, so firstly balance this. So let's do O last, because we can adjust oxygen last. So H is 6, here is 2, so let's put 3 in the front. C is 2, let's put a 2 in the front. And then we've got 4 oxygen and 3 oxygen. Here we've got 1 oxygen, so we need 6 more. All right, so what's important here is the ratio 1 to 3. So we need to find the moles of ethanol that we have. We've got 5 liters. That's not in molar ratio, so we've got to convert to moles. How do we do that? Well, we need the mass. Well, okay, so this is the density. This is the volume. So if you remember your density formula, mass over volume, we can rearrange. Now we can find the mass. Okay. 0.79 times. Now, careful, because this is in milliliters. So grams per milliliter, we want to answer in grams, so we've got to convert this to milliliters. Grams. All right, so now we've got maths. We can figure out the moles equals mass over molar mass. 3950 over. So use your periodic table. Okay, so you're going to find molar mass 2 carbon, 6 hydrogen, and 1 oxygen. 2 times 12.01 plus 6 times 1.01 plus 16. 3950 divided by, don't forget your brackets, 2 times 1 plus 6. Plus 85.72 moles. Right, so I've got moles and okay. Now, so how much oxygen do we need? Well, we're going to need so moles of O2 equals 85.72 times 3 because of the molar ratio. 257.16 moles of O2. Now, here they want the mass of air. So I guess we go back to mass now from moles. This is a bit extensive, isn't it? Mass equals moles times molar mass, 257.16. And mass of O2 is 32. 2 times 16 times 32. 8229.16 grams of O2. But that's not the answer either. They want a mass of air, and we know that oxygen makes up 21% by mass. So mass of air equals 8229.16 divided by 0.21. 39,186.5 grams of air. It's a lot of work, but if you show some of these steps here, you should be able to get most of those. Like, I mean, straight away you're getting marks for writing the equation down. You got the density. Now, another thing you can do, because right, you can get stuck. Let's say you forgot this step here, right? Don't give up. You just assume something. Okay, just jump straight down to here and just say, I'm just going to pretend, assuming 10 moles of O2 or something. Okay, so then you can demonstrate all these other steps. You won't get the same answer, but you lose 1 mark because you've made a mistake, but that mistake gets carried through. And so, yeah, don't just give up. Keep going. Just assume a number. And like, if you would just assume a number right from the start, a real easy number, you can throw away 1 mark and then make the whole rest of it really easy. And you should get 3 out of 4. Right. So we've got 2 isotopes of sulfur. This is calculate the relative abundance question. You should have practiced this type. It's expected to get this type of question. They're giving us a number slightly different to the periodic table, just so that you have to show working out. What's that working out? The first line is the relative atomic mass is equal to, well, because there's only 2 isotopes, we can say that the mass of 32 is 32. X is going to be the abundance of S32 as a decimal. Okay. We can see that. Okay. So, and then 34. If X, like if that was 100%, it would just be 1, right? But it's something less than 1, and so it's just the weighted average of these two. So 1 minus X. So if that's 0.9, this is going to be 0.1, because the 2 numbers together add to equal 1, 1 being 100%. All right, from here it's just a simple case of algebra. Expand. Collect like terms. 32 minus, just subtracting 34 from both sides, and then that's minus 1.91 is minus 2x. So x equals 0.955. Another thing, don't round the numbers here. Just, I mean, it's 95.5%. So, so therefore, and don't just leave it like this. Make some statement. So therefore, relative abundance of S32 is 95.5%. S34 is, well, that's minus that makes up the rest, 4.5%. State the number of protons, neutrons, and electrons. That's 16 protons. 34 minus 16 equals 18 neutrons, because that's the mass. Now careful here, because this has got extra electrons on it. Okay, so normally it would have 16, but we're going to say, because those two extras got 18 electrons. All right. Write the electron configuration in terms of shells and subshells. So this is the how many, you got to think how many we need. We need 18 electrons. Okay, so start off with your 1s2 and 2s2, 2p, now 6, so that's up to 10. How many do we need? 18. 3s2 and 3p6. 2 and 6 is 18. Just check it adds up. Okay. Okay. Since when sulfur and hydrogen react, S8 plus H2. Right, so, well, the two non-metals, when we're writing this, the hydrogen comes first. Now, if you're not sure, just start with S and allocate the electrons, the valence electrons. 1, 2, 3, 4, it's just like oxygen. Okay, and then you've got the hydrogen, 1, 1, so they form covalent bonds there. So it's H2S. Is the formula. What's the name for this? Commonly called hydrogen sulfide. But technically you could also call it dihydrogen sulfide as well. So either of those would be acceptable. We've got S3716 undergoes beta decay. So one of these protons, one of the neutrons becomes a proton. So that is the next one up, chlorine, same mass. But if you've got an extra proton, you got to balance that charge out with an electron. Okay, so that's the beta particle. Question 25. Right, just you can pause that and read it. It's a composition question with a little twist. There's two ways to do this actually. You could do it, but what I'll show you, like just treat it like any composition question. Start off, they give you the percentage. Let's assume this is 100 grams. So this changes it to grams. And now we just have to find out the moles of all this. So they don't give you a lot of working out space here, but okay, let's just divide it by 23.99 divided by 12.01 divided by 1.01 and divided by 16. Okay, let's just, this will tell us the mole ratio, 16.1. 0.6711, 4.2 divided by 12.01, 0.3497. Doesn't hurt to have a few extra decimals. 6.93, 72.7 divided by 16, 4.54375. Okay, which is the smallest one here? That's this one. So divide everything by 0.3497. Okay. This will give us whole number ratio, so that's obviously 1. That goes twice. 6.93 divided by 0.34. 19.8, let's call that 20. And 4.543 divided by, that's 13. So, okay, so let's have a think about this. Like, I'm sure this is quite familiar. Na2C1, what do you think it is? All right, let's pretend it's a carbonate, right? Sodium carbonate, 213, that would leave 10 left over, right? And then you've got, that would make 20 hydrogen and 10 oxygen. So how do you get 20 hydrogen and 10 oxygen? Well, Z would have to be 10. So that's kind of the quick way to do it. The other way is you could do the same thing, but start off with I mean, I'll show you this. This is probably the more typical way to do it. Let's do the same thing here. So divide by 23.99, divide by 12.8. We're still doing the same thing, finding the molar ratio, because this has been dehydrated now. Divided by 16. 43.4. So we're going to get the number of moles. We're assuming this is 100 grams. And so this is 1.809. 1, and then 11.3. 12.81. Fat fingers. 0.94. 0.88. 45.3 divided by 16. 2.83125. Which one's the smallest one? So we're going to find the ratio, whole number ratio. So that's 1, that's 2, and 2.83125 divided by 4. Okay, so that's 3, right? So that tells us sodium carbonate, right? Right, so now what we could do is we could say, well, we know that Na2 CO3 and some amount of XH2O, right? Well, let's just compare what we know, two things that we know. So we know in this example, we could compare the ratio of sodium to hydrogen, for instance, and that would tell us the ratio of X to Na, right? So I'm just going to get those two numbers. So just remembering that it's Na2 and H2. So how many moles of that is there? That is, can we see here? So we had 16.1 grams with a molar mass of, what is it? 22.99. Let's call it 46. And we've got 7 grams. 7 divided by 2.02, because remember it's H2. So let's see what we've got. 16.1 divided by 46. 0.35. 7 divided by 2.02 is 3. Let's call it 5. Okay. So this is obviously 10 times larger. So if you have 1 mole of this, we've got 10 moles of that. Okay. So here we have, they're giving us a number of reactions, a sequence of reactions. So we start with copper, and they tell us the reactants, but what they want. Read the question, because you got to give them what they want. You want equipment, outline the steps, so it's a procedure, balance chemical equations, and classify the type of reaction. Okay, so I don't think I'll write this out formally, but I'll just go through it. So so step 1, I'm just going to speak through it, okay, because it'll take me too long to write down. But so you want some small pieces, powderized metal would be good, in a beaker, okay, and then you're going to add, so we want excess copper, and we're going to add the silver nitrate. Why? Well, it's a add AgNO3 solution to copper in a beaker. Okay, and so I mean you want to put this in more steps here. So 1, but write the reaction. Okay, so copper plus AgNO3. Okay, and well, this is a displacement reaction. Okay, so we get copper nitrate plus silver. Okay, so this is a displacement reaction. How do you get the next step? We want the we'd have to decant or filter solution. Okay, so we don't want the silver. I'll let it sediment, write that down. And how do you get that next part? Question 2, we've got the copper nitrate now, and we are going to add sodium hydroxide. Okay, so let's write the equation down. So they want you to demonstrate like writing the equations. Copper nitrate plus sodium hydroxide is going to give us, what's that going to give us? Copper hydroxide, aqueous, solid, and sodium NO3, something like that. We're going to need 2 of those. Sorry, we need 2 of those. Okay, and balance them, of course. If you so what type of reaction is this? This is a double displacement, or you could call it a precipitation reaction. How do we get this solid in the end? And we would have to filter. Like you would be explaining this in more detail. Filter with filter paper and funnel, etc. So I mean, there's 7 marks here, so you can spend a bit of time on this. So how many steps do we want? We want 1, 2, 3, 4 major steps. So let's go to 3 here. Step 3. Now I'm just outlining it here. So how do we go from hydroxide to a copper oxide? Well, you can heat it. Okay, so heating copper hydroxide, and what do we have? Okay, so we've got thermal decomposition into copper oxide and water, and this is a decomposition reaction. H2O evaporates, solid, gas, solid. I also mentioned, so we mentioned the equipment, we're putting the equations down. The last step is going from CuO to copper sulfate. So what's the last reaction is the H2SO4. And what do you get? You get copper sulfate plus H2O. So we're getting a salt plus water. That's a neutralization reaction. All right. So you would say you're using beakers and as such. Okay. Question 27. Right, so we've got white phosphorus and red phosphorus. White phosphorus has a low melting point, red phosphorus has a higher melting point, what term do we give to different forms of the same element? Allotropes. Tropes. Allotropes. All right. On the basis of their melting points. All right. Well, if you don't, I mean, you could have a look at phosphorus. 1, 2, 3, 4, 5. How would it bond with another phosphorus? 1, 2. That, and maybe we could have another one. There's one. I mean, this looks like a okay, triangular pyramid. So that would be so you could say P4 is a molecule that, and it's balanced, non-polar, polar with dispersion forces as intermolecular bonds, which are weak, explains low melting point. P, so, well, it's something significantly stronger than these dispersion forces holding it. So you don't have to know this. It's just on the basis of the melting points suggest differences. The higher melting point suggests covalent bonds between red P. All right. And I mean, it probably should be say something like a giant covalent structure. Because it's not an ionic bond. Yeah. Okay, so that's the most relevant one. All right, so let's have a look at this. White phosphorus can be converted into red phosphorus according to this. We've got water. Calculate the final temperature of water. So this is a Q equals MCAT question. And this is for the amount of, what was it? Red phosphorus, P4, white phosphorus. So white, we're given 25 grams. So how many moles? Because this is for 1 mole of red phosphorus. So let's calculate how many. How many moles of yeah, let's calculate the moles of white phosphorus we have. So 25, so P4 moles of P4 equals 25 over 4 times, if you look up your periodic table, 30.97. (25 divided by 4). Oh, helps if it's on. Yeah. 0.202 moles of P4. Now what's interesting is we start with 0.25 moles of P4, so because we want to find out how much energy this heat is given off with our amount of white phosphorus. So 0.202 over, so we'll call, this is a heat calculation, divided by 0.25, which is the quarter of that, and heat is equal to times this here as a positive number. Okay, so 17.6 kilojoules. Okay, so we've got 14.22 kilojoules of heat from the 25 grams of P4. So now we can put that into our formula. So Q equals MCAT. We know that's 14.22. Now, what's the, how much did it heat the water? Well, let's say 100 grams. Now, just be careful because we've got to make sure, because this is in grams. So when we're looking at specific heat capacity of water, this is in, this one here is in kilograms. So it's not, so we could get rid of this. We only want the 4.18. 4.18. And we'll just find delta T, then sort out the rest later. Oh, wait a sec. We've missed a step here. So I'm kind of out of space, so a bit messy. Okay, but so because we lose 25%, we've got to shoot, it's lost. So we're assuming that this number is smaller. So times it by 0.75. So the amount of heat is 10.67 kilojoules. Q equals heat exchanged. So we'll just change that. 7. Okay, that should fix that up. Delta T equals 10.67 divided by, well, this is 418.67 divided by 0.0. Wait a second. Okay, so it's not, I've just noticed it doesn't make sense. It's too small a change. So this is in joules. Okay, so I should convert this to, this is in kilojoules here. So I need to change that to joules. And let's try that again. Okay, so delta T is 25.52. And if delta T is equal to the temperature final minus temperature initial, and temperature final, and what it was, 22, wasn't it? Here we go. And 25.5. Okay, temperature final is 47.5 degrees Celsius. All right, use the data in the equation below. All right. To predict if it's spontaneous. So this is a Gibbs question. Write the equation. Let's just start off there before you even think of anything else. Delta H minus temperature delta S. And where do we get this from? Well, here's delta S. Here's delta H. Okay, so minus 17.6. Don't forget it's kilojoules. Minus temperature 25 degrees. This is in Kelvin, so that's 298 Kelvin times this number here. Now this is in joules, so we've got to move the decimal place 3 times. Hang on. That's a negative. I mean, sometimes what you want to do is, like I've got a number, I just want to see what this side of it is. 298 negative 298 times. It's easy to like press the wrong button. So that is, like I just did then, apologies, minus 298 times minus 0.105. So that's 31. This is bigger, so plus 31 is bigger than this. So we know the answer has to be positive. So our value is plus 13.81 kilojoules per mole. If Gibbs is positive, therefore delta G is positive and not spontaneous. All right, let's keep going. When a high voltage electric current is passed through hydrogen gas, light is produced. Okay, so you can use diagrams firstly. So explain how the Bohr model of the atom is useful for accounting for the unique spectral lines of hydrogen. Okay, so hydrogen, it's only got one electron, but when it gets energized and bumped up, when it comes back down, it emits a photon of discrete frequency. Is when energized. These discrete energies match frequencies match spectral lines. It's useful. How's it useful? It's useful because the Bohr model can predict expected lines of an element. Okay, something like that. Hydrogen has 3 known isotopes. Would you expect the spectra of the isotopes? Well, look, there's 2 answers here, and both of them, I'd pay both of them because, well, firstly, isotopes have the same electron configuration. So isotopes have the same electron configuration. Therefore, I'd expect emission spectra of isotopes to be identical. So what I've done is I've justified my answer. Now, it turns out that emission spectra is pretty much the same between isotopes, but it's not. There is a slight shift. It's not really even. It's not noticeable, really. But there is a small shift. So you could have said here that due to due to different masses of nucleus, the energy levels of shells are slightly different, resulting in minor change in emission spectra. Okay, so he could have got, it didn't really matter what you said as long as you justified it. Goldine, okay, 2 marks, explain. So Goldine looks like this. Explain why striking, if you just want to read it, maybe pause. And explain why striking it. And so a nugget of gold has metallic bonds in 3 dimensions, making it have malleable physical properties. Goldine, I mean, it looks like they're covalent bonded. They're not really. Like, I don't know much about goldine. But the way they've depicted it shows it doesn't look like a metallic bond. Appears to have covalent bonds in 2 dimensions, like graphene, okay, which is this would give it different physical properties. Like brittleness. Okay. Use the information provided above. So, all right. So they're asking us to analyze a 10 by 10 nanometer. How many gold atoms? So let's just count from here. Oh, okay, so what, from here to here? Yeah, I guess it doesn't matter where you go, because you got 1, 2, 3, 4 atoms. 1, 2, 3, 4. So if 1 nanometer has 4, this length would be 10 nanometers would have 40, right? And this would be the same here. So 40 by 40, 1600 atoms. The moles it contains, well, that's there are how many atoms in a mole of something? Well, that's Avogadro's number, 6.022 times 10 to the 23. Okay, so the moles of gold, well, that would be 6.022 times 10. Sorry, 2.656. That's 66 times 10 to the minus 21. Now, again, like, if you don't know something, just keep going, okay? You could assume this and then do this question here. Like, if you forgot this number, just make up a number here and then do the next bit. Okay, 2.66. What's the mass of this? Well, if you look at gold, 197, yep. So mass is equal to moles times molar mass. 2.66 times 10 to the 20 minus 21 times 197 times 197. 5.23 times 10 to the minus 19 grams, because it's grams per mole. And that's it. Okay, so good job, guys. It was a tricky one. A lot of calculations in there from earlier in the year, but I hope you just make sure you learn from your mistakes, and then you'll be better for it. Okay, good luck.